Okay, so I want to start today with a concept that, well, it honestly feels like it violates the most fundamental rule of machine learning.
Oh, absolutely.
If you talk to anyone who built neural nets, 5, 10 years ago, even 3 years ago, they'd all tell you the same thing.
Yep. Training is for learning, inference is for working, period.
Exactly. You train the model, you freeze the weights, you set its brain in stone, and that's it. It never learns another new thing. It's just a static object.
That was the dogma. You burn millions of dollars to bake the cake, and once it's out of the oven, you can't change the ingredients. The model is done.
Right. But then you have today.
Yeah.
You open a prompt window, you give a big model a completely made up language
Yeah.
or some weird logic puzzle it has definitely never seen before.
Something totally out of its training data.
Totally. You give it 3 examples
Yeah.
and it solves it. It learns instantly without changing a single one of those frozen connections.
It's the paradox of the frozen learner. I mean, it shouldn't be able to adapt, but it's maybe the most adaptive software we've ever built.
So, how is that possible? How can a frozen brain learn? That's the mechanism we are taking apart today.
We're looking at a paper that really digs into this.
Yeah, it's titled In Context Learning as General Purpose Learning, published just last year, 2025, by Fan Wang and a team from the Shenzhen Institute of Artificial Intelligence and Robotics.
And I think it's important to say up front, this isn't just a paper about how to write better prompts or something.
No, not at all. They're arguing that this thing, in context learning, or ICL, it isn't just a quirk, it's a fundamental shift.
They're saying we are accidentally building a, what do they call it? A general purpose learning engine. And it works completely differently than we thought AI worked.
General purpose learning engine. That's a heavy phrase. So our mission today is to figure out what is physically happening inside that model, why it matters for things like, say, robotics, and why the authors think our current tests are basically lying to us.
It's a deep one for
Yeah.
sure, but the implications are, well, they're massive.
Okay, let's start with a definition. When we say in-context learning, I think most people's minds go to few-shot prompting.
Right.
I show the AI a pattern. France is to Paris, Spain is to Madrid, and then I ask it to finish Japan is to. That's ICL, isn't it?
It is, on the surface, yeah. But the paper asks us to look deeper at the architecture of that learning. They call it a bi-level framework.
Yeah, a bi-level framework.
Yeah, just think of it as two loops running at totally different speeds.
Okay, 2 loops. Break that down for me.
So the first loop is the outer loop. That's your traditional training. It's slow. You've got a huge data set, an optimizer. And over weeks, maybe months, you're slowly nudging the model's parameters. Let's call them theta.
Theta. Yeah.
This is like evolution. It's slow, it's permanent, and it sets the innate capabilities of the model.
So the outer loop is like millions of years of evolution, packing instincts into DNA. And once that training run is finished, the DNA is set. Theta is locked.
Exactly. But then you have the inner loop. This happens at runtime,
Yeah.
when you're actually using the model.
Okay.
You feed it a sequence of data, a context. The model takes that context, and it creates a temporary state. The paper calls it phi. And this phi is effectively a little specialized model that just spun up for that one interaction.
Okay, wait. Can I stop you there?
Yeah.
Because this is the part that always gets me.
Go for it.
You're saying it creates a temporary state, this phi.
Yeah.
Where does that live? If the weights, the theta, aren't moving, where is this new information being stored?
That's the million-dollar question, right? And it's actually pretty concrete. Physically, inside the GPU, this all lives in the activations and the memory cache, specifically something called the key value cache.
So it's not rewriting its hard drive.
No, not at all. It's more like it's configuring its RAM into a specific tool based on what you just told it. It uses its frozen permanent knowledge to process a new experience into a temporary skill.
So the outer loop gives it the ability to learn, and the inner loop is the act of learning in real time.
Yes. And the paper makes this amazing connection to meta-learning here. The outer loop isn't really teaching the model facts. It's teaching the model how to learn from the inner loop.
It's learning to learn.
Exactly. The goal of that massive training run isn't to memorize Wikipedia. It's to build an engine that can understand a new Wikipedia page the moment it sees it.
That's a huge difference. We aren't teaching it to translate French. We're teaching it to spot a translation pattern and then just apply it, whatever the language might be.
Precisely. And because of that, the authors say ICL has evolved way beyond just, text in, text out.
Right.
The taxonomy they lay out in the paper is so much broader. They break down how this learning engine is being used for things that look nothing like a chatbot.
I was really struck by the section on in-context reinforcement learning, ICRL.
that stuff is mind-bending.
Because I think of reinforcement learning as an agent playing a game. It tries something, gets a score, updates its brain, tries again. How can you do that inside a frozen prompt?
So in ICRL, the prompt isn't a static set of instructions. It's more like a history log, a game tape.
A log.
Yeah. The model looks back at its own recent history in the context window. Okay, at time step 1, I saw this, I did that, I got a penalty. Okay, at time step 2, I tried this other thing, and I got a reward.
So the learning is just the model analyzing its own recent successes and failures right there in the text.
Yes. It's running a little optimization algorithm just using its attention mechanism. It learns to pay more attention to the high-reward moves in its history and to ignore the behaviors that led to penalties. It improves its strategy on the fly.
Without a single weight update.
Not one. That sounds so much more efficient than having to retrain a model every time you want to change its behavior.
It is. The context is the training. And it also solves another huge problem in AI.
Catastrophic forgetting.
Right. Explain what that is for anyone who might not know.
In a traditional network, if you train it on task A and you try to train it on task B, it tends to overwrite the knowledge for task A. It forgets the first thing to learn the second.
But with in-context learning,
You're not touching the weights. So you can stack tasks. This is what the paper calls in-context continual learning.
you can just keep adding new tasks to the context window and it never forgets the old ones.
As long as your context window is big enough, yeah. It just keeps appending to that temporary phi state. It never overwrites anything.
They also talked about reflection and chain of thought as a form of ICL. I use chain of thought all the time, telling the model to think step by step. I never thought of it that way.
But it is. Think about what's happening. When the model outputs step 1, I need to calculate X, that sentence immediately becomes part of the input for the very next word it generates.
It's feeding its own reasoning back into its own context.
It's talking to itself to create the learning material it needs to solve the problem. The paper calls it autoregression as a feedback loop. It's building a scaffold of logic in its working memory.
Okay, I want to go back under the hood. We mentioned the key value cache, the RAM, where all this learning lives. The paper points out a huge bottleneck here.
The memory problem.
Yeah.
In a standard transformer, like a GPT-4, the memory is what they call internal extensible. Meaning, every new word you add to the conversation adds to that cache. It's very precise, you remember everything, but it's incredibly heavy on the hardware.
It scales linearly, right? A long conversation just chews through GPU memory.
A massive problem if you want an inner loop that can run all day, like on a robot. So the paper says we're moving toward internal compressive memory.
They mention things like titans and linear attention. So what's the difference there?
The current way is like a court stenographer writing down every single word.
Mm.
It's accurate, but you get thousands of pages. Compressive memory is more like a good secretary taking minutes.
Ah.
You compress the long history into a fixed size state.
Mm.
You keep the gist, the essential variables.
So you lose a little bit of the detail, but you can run forever.
That's the trade-off. And the paper argues that for true general-purpose learning, we need these new architectures that can summarize experience without losing the crucial bits.
You can't forget why you got that penalty 3 steps ago.
Exactly.
Now, there was one distinction in this paper that I think I circled it 5 times. The difference between task identification and task learning.
Yes. This is the humbling part of the paper.
It feels like this is where the authors are kind of calling us all out.
They really are. They're forcing us to ask, is the model actually learning? Or is it just a good actor?
Okay, break it down. What's the difference?
Task identification is when the model sees your examples and basically goes, oh, I know this. This is a translation task. I learned how to do translation during my big training run. Let me just activate those circuits.
So it's not learning anything new. It's just recognizing a skill it already has.
Correct. The paper calls this in-weight learning. The context you provide is just a key to unlock a pre-existing skill. But task learning, that's different.
It's the real deal.
That's when you give the model a function it has truly never seen. The answer is not in its weights. It actually has to look at the input-output examples you gave it and synthesize a brand new algorithm on the fly.
Give me an analogy.
Task identification is you sitting at a piano and playing Happy Birthday. You memorized it years ago. Task learning is you seeing a sheet of music for some weird avant-garde piece for the first time, analyzing the notes, the timing, and then playing it. You're learning it from the context.
And the paper's big claim is that most of what we think is learning in LLMs is just identification.
Mostly, yes. They suggest that true task learning needs what they call many-shot learning. hundreds, maybe thousands of examples in the prompt to really force the model to build something new.
Which leads directly to the benchmarking crisis they talk
Yeah.
about. If we can't tell the difference between the model remembering something and the model actually learning something,
Well,
how do we know if they're getting any smarter?
we mostly don't. The authors are really critical here. They say if you test a model on classifying movie reviews, well, it saw millions of movie reviews during training. That isn't a test of intelligence. It's a test of recall.
It's a vocabulary test pretending to be an IQ test.
Perfectly put. They're calling for us to use more synthetic tasks, made-up languages,
Yeah.
weird logic gates, things that you can guarantee the model has never seen. Only then are you actually measuring the power of that inner loop.
So let's talk about the why. Why does this happen at all? We didn't program an inner loop into these things. We just told them to predict the next word over and over.
Right.
So why does predict the next word magically turn into learn how to learn?
This is the outer loop incentives part of the paper. And it turns out ICL is just the most efficient strategy for the model to survive the training process.
It's a survival mechanism.
It is. The paper identifies two key properties of data. The first is burstiness.
Which sounds like a type of candy.
It does. But it just means that in any real text, words and concepts cluster together. If we're talking about in-context learning, we're probably going to keep saying in-context learning for the next 10 minutes.
We're not going to suddenly start talking about, I don't know, penguins.
Right. The data stays on topic, so the model learns a shortcut. Hey, to predict the next word, the best clue is just the last few words that were said. It learns to rely on recent history.
So it gets efficient.
It gets efficient. It uses the context to reduce surprise. But then there's the second factor, which is task diversity.
The opposite of burstiness, right?
Kind of. This is about how different documents relate to each other. If every single document in your training data was, say, a legal contract, the model would just memorize the rules of legal contracts. That would be in-weight learning.
But the internet isn't like that.
Not at all. One page is Python code, the next is a Shakespeare sonnet, the next is a recipe. The rules are constantly changing from one sequence to the next.
So the model can't just memorize one single set of rules.
It can't. The only way for it to get a low error rate across all that chaos is to become adaptive. It's forced to develop that inner loop so it can figure out the local rules of whatever document it's currently in.
Wow. So the messiness of the data is what forces the emergence of this reasoning-like ability. It's adapt or die.
That's a great way to put it.
Okay, before we wrap, we have to touch on the physical world. The paper talks about embodied AI. How does any of this apply to a robot?
This is where it all comes together. Vision, language, action. Think about a robot in a warehouse. Normally, to get it to pack a new type of box, you'd have to write a ton of code.
Or run thousands of hours of simulation.
Right. But with ICL, the idea is you could just show the robot a video of a person packing the box. That video becomes the context.
The robot watches the video.
It analyzes the movements, maps the human actions to its own joints and motors, and then it just does the task.
So it's many shot prompting, but the shots are video frames and the output is motor commands.
Exactly. It's the ultimate generalization. You wouldn't need to retrain the robot for every new product. You just give a new context.
Yeah.
But, and it's a big but, the paper is clear that ICL is still very brittle.
Generalization uncertainty.
Right. You change the camera angle, you change the lighting, and the whole thing might just fall apart.
Right.
The inner loop isn't stable enough for safety-critical hardware. Not yet.
It does bring up this really provocative idea that the authors end with, basically, the death of training.
It's a radical thought. They're suggesting that as these inner loops get more and more powerful and our context windows get bigger and bigger, the role of that slow, expensive outer loop just shrinks.
Meaning we stop trying to bake knowledge into the model itself.
Exactly. We just train a really, really good learner. We build a blank slate, a tabula rasa, that's just incredibly good at processing context. And then if you want to lawyer AI, you don't spend a year training it on law books.
You just feed the entire law library into its context window when you turn it on.
The knowledge becomes the fuel, not the engine. And that flips the entire economic model of AI on its head.
It's not about who has the best model weights anymore.
It's about who has the best, most curated context data. The model becomes a commodity. The context becomes the asset.
That's a complete inversion. We've been obsessed with model size, the number of parameters, but maybe we should be obsessed with context quality. It changes the game from who has the biggest brain to who has the best library.
That's the takeaway. We're moving to a world where programming is really just curating experience.
We've covered a lot of ground. From the paradox of the frozen brain to the two loops of learning, the mechanics of memory, and the huge difference between remembering a task and actually learning it.
It really reframes everything. You start to see every prompt not as a command, but as a curriculum.
And that's the thought I want to leave everyone with. The next time you're pasting a few examples into a chatbot to get it to do what you want, just realize what you're actually doing. You aren't just giving it instructions. You are designing a temporary brain. You are the architect of that inner loop. So the question is, are you building a good one?
That is the question.
Thanks for diving deep with us. We'll see you next time.
Goodbye.